Today, when you pull out your phone to find a coffee shop, a glowing blue dot tells you exactly where you are. We take that certainty for granted, but for most of human history, figuring out your location was a deadly guessing game. Imagine waking up in the middle of the night in a pitch-black house. To get to the kitchen, you have to guess how many steps you've taken and which way you've turned, reaching out blindly in the dark. That is how sailors used to navigate the oceans. They called it dead reckoning. Without landmarks to guide them, they estimated their current position based on the direction they had been steering and how fast they thought they were going. The danger of that guesswork became clear in 1707. A British naval fleet was sailing home through heavy gales, and the rough weather pushed them off their estimated course. Because of that minor mathematical error, the fleet headed straight for the rocky shores of the Isles of Scilly. 4 warships struck the reefs and sank, and up to 2,000 sailors drowned in the freezing water. Even with the industrial advances of the 20th century, this vulnerability persisted. In 1923, 14 United States Navy destroyers were steaming south toward California. On a single foggy night, 7 of those steel ships plowed directly into the coastline. They were lost because of identical errors in their dead reckoning. Human estimation is fragile. Relying on past movements to predict current locations led to thousands of lost lives. The world needed an infallible external reference point to guide us. A potential solution arrived with the space race. In 1957, the Soviet Union launched Sputnik. As the United States military tracked its radio signals, they realized they could use orbiting satellites to figure out exact positions down on Earth. GPS works by carrying ultra-precise atomic clocks, like these early models, into orbit. Think of how GPS works like a giant game of Marco Polo. A satellite shouts Marco by sending a radio pulse downward. Your phone hears it and yells Polo. Because radio waves travel at the speed of light, the system logs the exact fraction of a second that signal took to arrive, calculating exactly how far away you are. One satellite gives a broad distance, but when your phone listens to 4 different satellites at the same time, those time signals cross-reference. Where those expanding circles of signal perfectly overlap, that is your exact physical location. For this geometry to work, the clocks on those satellites have to measure time down to the nanosecond, 1/1000th of a second. GPS functions as a highly synchronized cosmic timekeeping system, floating high above our heads. But placing perfect clocks into orbit introduced a massive physical hurdle. To make the system work, engineers had to confront the theories of Albert Einstein. Einstein's theory of general relativity shows that time is not absolute. Because GPS satellites orbit far away from Earth's gravity and travel at extreme velocities, time literally passes faster for them than it does for us on the surface. The math reveals an exact discrepancy. Every day, the clocks on those satellites run 38 microseconds faster than the clocks here on Earth. If engineers ignored that tiny fraction of a second, the timing signals would drift out of sync. Within a single day, your phone's navigation would be off by miles, rendering the whole system useless. To keep us on course, engineers have to constantly write software to actively slow down the satellite clocks. Einstein's abstract theories became a practical, daily requirement for this technology to function. Even after engineers conquered the physics, this navigation network was initially a strictly military tool. Then, in the September of 1983, a civilian aircraft, Korean Airlines Flight 007, was traveling from Alaska to South Korea. Using an error-prone navigation system, the plane accidentally drifted off course into prohibited Soviet airspace. The Soviet military mistook the passenger plane for an American spy aircraft and shot it down. All 269 people on board died. The tragedy caused massive geopolitical fallout and protests worldwide. 2 weeks later, President Ronald Reagan announced that the United States would share the facilities of its GPS network with global civil aviation to prevent such an accident from ever happening again. But there was a catch. For the next 17 years, the military still intentionally scrambled the civilian signal. Under a policy called selective availability, public users received a fuzzy version of the data, while the military kept the highest accuracy for itself. That dual-tier system finally ended in May of 2000, when President Bill Clinton signed an order to permanently disable the scrambling, giving everyone access to the system's full precision. The impact was immediate. Suddenly, everyday civilians and rescue operations possess the same navigational clarity once reserved for the military. When you watch that blue dot smoothly track your progress on a digital map today, you are seeing the results of a centuries-long struggle to overcome the dangers of navigating by guesswork. Our everyday digital convenience was paid for by nautical tragedies, the brilliant physics of time-bending clocks, and the intense diplomacy of the Cold War. You open a map app, wait a second, and a blue dot appears on the screen. We've come to trust that dot implicitly to tell us exactly where we are. But generating that dot in a single second requires your phone to communicate with a multi-billion-dollar constellation of over 30 space robots orbiting the planet. To find your location, your phone relies on trilateration. It has to lock onto signals from at least 4 satellites simultaneously to calculate your latitude, longitude, altitude, and the exact time. By measuring how long a signal takes to travel from space, the system creates intersecting spheres of probability to find your exact point on the surface. To guarantee 4 satellites are always visible, the constellation is distributed across 6 specific orbital planes. This geometry is perfect on paper, but it assumes the signals are moving through a vacuum. In reality, the physical universe actively works to disrupt the system. Making navigation feel this simple required engineers to solve for the persistent, chaotic variables of the physical universe. The staging ground for this geometry is medium Earth orbit, roughly 20,000 kilometers above the Earth. Orbiting at this altitude forces the satellites directly into the Van Allen radiation belts, zones where high-energy particles are trapped by the planet's magnetic field. This environment is hostile. Intense radiation can destroy delicate electronics and the sensitive atomic mechanisms used for timing. Engineers like James Spilker had to develop stringent shielding standards to harden every component, so they could survive for years in a radioactive vacuum. But even with indestructible hardware, the radio signal itself faces a massive physical barrier as it travels back down to Earth. A radiation-proof satellite is ultimately useless if the signal it transmits gets corrupted before it reaches your phone. Although the GPS signal travels at the speed of light, it crashes into Earth's ionosphere and physically slows down. This atmospheric drag bends the radio waves, delaying the data your phone needs to calculate distance. In a system based on timing, a delay of just 1 millisecond in the sky translates to miles of physical location error on the ground. To fix this, scientists use the Klobuchar ionospheric model, a mathematical software correction built into the system. The model calculates the exact atmospheric drag in real time and injects a correction into the navigation message to keep the signal on target. While software can adjust for atmospheric noise, it has no power over the way gravity and velocity distort time itself. The most significant threat to GPS accuracy comes from Albert Einstein and his theory of relativity. Because gravity is weaker far from Earth and orbital speeds are so high, time physically passes differently for the satellites than it does for us on the ground. The result is that the atomic clocks on board the satellites run exactly 38 microseconds faster every single day. If engineers ignored this, that 38 microsecond drift would cause a phone's location to move by 10 kilometers every 24 hours. To solve this, engineers intentionally set the clocks to run slowly while they are still on Earth, knowing that the physics of space-time will speed them up to perfection once they reach orbit. The entire navigation system relies on deliberately manipulating the distortion of time. Because we successfully navigated the challenges of radiation, the atmosphere, and relativity, GPS now operates as an invisible global utility. This atomic precision provides the timing infrastructure for global cellular networks, for power grids, and financial markets. The Space Force continues to maintain this backbone, recently deploying the final GPS-3 satellites to increase both security and accuracy. Following a blue dot on a screen is only possible because a shielded clock, 20,000 kilometers away, is hacking the universe to tell you when to turn left. You're hiking miles from a cell tower, and you switch your phone to airplane mode. You open your map, and the blue dot is right there, tracking your exact movements. Most people assume that tracking dot requires a cellular or Wi-Fi connection. It doesn't. Your phone's GPS is a completely passive receiver. It calculates your coordinates entirely offline. Your device never actually sends a signal up to a satellite. It simply listens for a one-way broadcast falling from the sky. Because it only receives, turning off your data doesn't stop the tracking. Short of wrapping your phone in a Faraday cage, it keeps listening. To generate that location without the internet, your phone is catching a faint radio whisper transmitted from 20,000 kilometers out in space. And getting that signal to your screen requires overcoming massive physical and mathematical hurdles. The process starts in medium Earth orbit. Up here, navigation satellites broadcast a continuous radio signal containing just two pieces of information: the exact coordinates of the satellite and the precise fraction of a second the signal was transmitted. Your phone measures the signal's arrival time to calculate distance, but one measurement only places you on a massive sphere. A second and third satellite narrow the overlap to 2 points. A fourth satellite locks down your exact position on Earth. These radio waves travel at light speed. If the time measurement is off by a single millisecond, your calculated position shifts by 300 kilometers. To maintain that required precision, navigation satellites are equipped with atomic clocks. They are the most accurate timekeeping devices ever built, ensuring the timing data sent back to Earth is virtually flawless. But there's a physical complication. Because satellites move fast and experience weaker gravity than on the surface, time actually moves differently for them. Their atomic clocks naturally tick at a slightly different rate than clocks on Earth. If ground control stations didn't upload timing corrections to account for relativity, your blue dot would drift off target by 11 kilometers every single day. Maintaining accuracy requires us to constantly account for the reality that space and time behave differently in orbit than they do on the ground. Once the signal survives the journey through the atmosphere, it hits a severe bottleneck. The radio broadcast is incredibly faint, and it transmits data at an agonizingly slow 50 bits per second. If you rely entirely on that space-based signal, a standalone receiver needs a clear view of the sky for 12.5 minutes just to download the satellite orbital data, the almanac, and calculate its first location fix. This is where your cellular network steps in. A system called Assisted GPS, or AGPS, bypasses the slow satellite link by downloading the heavy orbital data over high-speed internet. A nearby cell tower feeds that prepared data directly to your phone. It effectively warms up the receiver, dropping the wait time for a location fix from several minutes down to a few seconds. This hidden cellular assist is why we falsely assume GPS requires the internet. We trade offline independence for the instant convenience of a fast connection. This graphic shows the final physical barrier, the urban canyon. Entering a dense city creates a brutal environment for weak satellite signals. The orange lines represent multipath propagation. Bouncing off concrete and glass skyscrapers, they feed your phone a chaotic mess of ghost signals. This chart shows the first layer of defense. By combining the American GPS network with international systems like Russia's GLONASS, the receiver dramatically increases the number of visible satellites it can track in those narrow strips of open sky. This map shows the results of a modern software fix called SmartNav. It uses Google's 3D building data and advanced wave analysis to actively filter out those bouncing echoes, plotting a precise path with 10-centimeter accuracy. Navigating the urban canyon requires merging raw radio signals from space with sophisticated ground-based architectural mapping. That simple blue dot on your screen represents the real-time culmination of atomic timekeeping, cellular data rescues, and 3D wave filtering. Even when you're offline, background apps like fitness trackers and maps can continue to calculate these coordinates and store them in your phone's internal memory. This creates a detailed log of your precise movements that is automatically synced to the cloud the moment you reconnect, turning a passive signal into a permanent record of your private life. Mastering this obstacle course is mandatory for the future of transportation. The hyper-precise, multi-layered navigation system is the only way autonomous vehicles will be able to safely navigate complex city environments. The next time you open your map app, recognize what is happening behind the glass. You are holding a device that actively compensates for the laws of space and time, just to tell you which way to walk. Humanity has always sought to pinpoint its exact location on Earth. Over time, the physical tools we built for wayfinding have evolved into an invisible infrastructure in orbit that dictates the rhythm of the modern world. Before satellites, navigation relied on human observation. We used physical landmarks and calculated our routes on static paper maps to find our way from point A to point B. The mid-20th century brought a major technological leap forward. During World War II, systems like the British G and American LORAN allowed navigators to determine their position using precisely timed radio signals broadcast from ground stations. As this diagram shows, ground-based radio navigation carries a strict physical limitation. As radio waves travel from their source, they fan outward. Over long distances, the signal spreads, creating a massive margin of error. To achieve true global accuracy, engineers had to bypass the limitations of ground-based transmitters and move the technology into space. Today, the Global Positioning System consists of a synchronized network of 24 to 32 satellites operating in semi-synchronous orbit around the planet. Through trilateration, a ground receiver calculates its exact position by measuring distance from at least 3 satellites simultaneously. Each satellite carries an atomic clock. Measuring the signal's time of flight to a fraction of a second pinpoints a location with centimeter-level accuracy. GPS is an omnipresent web controlling massive physical systems. This level of synchronization dictates our global logistics and infrastructure, but it carries a hidden biological cost. That invisible web extends to the most extreme, chaotic natural environments on the planet. On Svalbard's Nordenskjöld Glacier, scientists deploy standalone, single-frequency GPS receivers directly into the ice, leaving them to operate continuously for years at a time. By tracking the ice's hourly velocity, these receivers capture exactly how seasonal meltwater accelerates the physical movement of the glacier downstream. Beyond passive monitoring, GPS allows for active physical control over massive plots of land in precision agriculture. Farmers use automated steering systems accurate to within 2.5 centimeters. This ensures every pass across a field perfectly aligns seeds and levels the terrain, virtually eliminating wasted fuel, fertilizer, and water. Satellite precision has taken unpredictable natural environments and converted them into mathematically managed, highly efficient grids. In the built environment, this same technology acts as the invisible backbone of the global supply chain. Logistics networks geofence their cargo to optimize international delivery routes. By tracking exact movements in real time, companies verify deliveries and prevent billions of dollars in cross-border theft. Large-scale engineering projects also depend on this constant spatial awareness to remain intact. Automated GPS sensors mounted on infrastructure detect millimeter-level sway caused by ambient wind or temperature shifts, triggering alarms long before a structural failure occurs. Because this optimized system handles the heavy lifting of wayfinding, human operators are rarely required to know where they are. We simply follow the automated prompts directing our every move. This automated precision allows our infrastructure and logistics to run with minimal human oversight. However, this reliance sets up a dangerous paradox for our internal biology. As this diagram illustrates, human navigation begins in the hippocampus. This region of the brain is responsible for episodic memory and spatial mental mapping. In 2020, Montreal researchers tested drivers to see how relying on GPS impacted their neurological function. They found those heavily dependent on satellite navigation exhibited severely reduced activity in the hippocampus, struggling to build mental maps linking physical landmarks together. Instead, these drivers relied on a stimulus response mechanism. It acts as a mental autopilot, where a person merely reacts to an instruction to turn left or right without any real understanding of their broader location. Just like an unused muscle, an unengaged hippocampus actively atrophies and weakens over time. The more perfectly our external technology maps the world, the more our internal biological hardware physically degrades. You can observe the opposite effect in people who still rely entirely on physical spatial memory, like traditional London cab drivers. To pass their grueling licensing test, known as the knowledge, these drivers memorize thousands of individual streets and routes. That intense mental exertion physically strengthens and enlarges their hippocampi. The hippocampus serves as the anchor for our broader human identity, linking physical locations to the deep personal experiences that define us. Outsourcing wayfinding to an infallible web of satellites threatens our biological capacity to generate these foundational experiential memories. Humanity succeeded in building a perfect centimeter-accurate map of the Earth, but in doing so, we are slowly erasing the map inside our own minds. Global infrastructure operates on a strict dependency, the continuous reception of radio frequency timing signals from GNSS satellites. But place a receiver in a dense urban canyon or a subterranean tunnel, and that dependency violently breaks. Under ideal conditions, GNSS calculates your position through trilateration. It requires a clear, direct line of sight to multiple satellites, relying on the exact time those radio waves take to travel from orbit to your device. The terrestrial environment severely distorts that geometry. Buildings, mountains, and even wet ground physically intercept and scatter the incoming radio waves, creating an error known as the multipath effect. This diagram illustrates the mechanics of multipath interference. A receiver picks up both the direct path from the satellite and longer, indirect paths that bounce off a reflecting surface before reaching the antenna. The first specific type of multipath error is diffuse forward scattering. This occurs when a signal hits a widely distributed area, like rough terrain, breaking the wave into a disorganized spread of delayed arrivals. The second type is specular reflection, when a signal bounces off a smooth, well-defined object, like a building facade or a body of water. It arrives at the antenna intact, but critically delayed compared to the direct path. Because the receiver relies entirely on time of flight to calculate distance, a delayed signal registers as a false physical location. The physical environment itself dictates the failure of the GNSS framework, driving the need for absolute reference alternatives. To understand why this is difficult to correct, we must look inside the receiver's tracking loops and examine the mathematical errors multipath generates. This chart graphs signal error thresholds, showing how heavily pseudo-range code measurements are impacted. When multipath interference hits, the pseudo-range calculation experiences a massive positional error spike, usually jumping by 1 to 5 meters. Carrier phase measurements operate under much tighter tolerances. Under the exact same multipath conditions, the carrier phase noise remains constrained to a narrow margin of just 1 to 5 centimeters. But this creates a severe operational trade-off. Because the carrier phase wavelength is so short, the tracking loop struggles to maintain a lock. Under heavy interference, the highly precise signal frequently fractures or drops out completely. The severity of these errors is also tied to satellite geometry. Signals arriving from satellites at lower elevation angles must cut through more of the local environment, making them highly susceptible to path differences compared to high elevation signals. Engineers use standard software filtering to try and smooth out these positional spikes. However, algorithms cannot erase the physical reality of a delayed radio wave. Signal filtering eventually hits a hard physical limit. Achieving continuous precision in a denied environment requires abandoning external radio reception entirely. The established fallback for GNSS loss is autonomous tracking using a classical inertial measurement unit, or IMU. These systems use internal accelerometers and gyroscopes to calculate changes in direction and speed without external input. A classical IMU's mechanical flaw is computational drift. Minute sensor imperfections accumulate, causing the estimated position to drift from the true location. Without GNSS updates to correct the math, this drift compounds exponentially, degrading the navigation solution into a massive probability cloud. Solving this is not a simple matter of building better hardware. Sensor engineering is governed by strict constraints known as SWaP-C: size, weight, power, and cost. Building a classical IMU precise enough to eliminate drift requires components so large and expensive that they violate SWaP-C limits, making them entirely impractical for continuous operations on mobile platforms like submarines or aircraft. Classical hardware cannot operate indefinitely without an absolute external truth. To find a reference point that never drifts, engineers have turned inward to the invariant properties of subatomic particles. Quantum sensors operate on a different physical baseline. Because the fundamental properties of particles, like atoms or photons, do not change, measurements built on these properties are inherently bias-free. This table highlights two primary techniques. First, cold atom interferometry isolates ultra-cold atomic clouds, functioning as a highly precise, GPS-independent quantum inertial measurement unit. The second major technique utilizes nitrogen vacancy centers, an atom-like defect structured within a diamond lattice. NV centers respond to magnetic fields with remarkable accuracy at room temperature. They can map the Earth's crustal magnetic field to provide an unjammable, absolute reference grid. Currently, these quantum sensors cannot function completely alone. They require a fusion architecture, pairing highly stable quantum measurements with classical tracking systems to operate in the field. This graph shows trajectories from a phaser quantum flight test. Over a 1,000-kilometer route, the INS-only trajectory, marked by green arrow ellipses, suffers a massive error bloom. The hybrid system's red line achieved a 50 times reduction in error. By fusing classical motion tracking with the absolute properties of quantum states, engineers have successfully decoupled terrestrial navigation from satellite dependencies. At the interplanetary scale, the rules change entirely. When a spacecraft leaves Earth orbit, standard GNSS vanishes, and mapping crustal magnetic fields via NV centers is no longer relevant. For missions traveling to the Moon, Mars, and beyond, the sole lifeline for positioning and timing is NASA's Deep Space Network. The DSN relies on 3 primary antenna complexes. Placed roughly 120 degrees apart across the globe, this architecture bypasses the Earth's rotation to maintain a constant, unbroken line of sight to distant probes. Unlike a terrestrial receiver, a deep space probe cannot calculate its own position locally. It must be actively tracked by ground stations on Earth using strict kinematic analysis. First is ranging. Measuring the exact time delay of a radio pulse traveling to the spacecraft and back calculates precise distance. Second is Doppler shift. Analyzing the returning signal's frequency calculates the probe's radial velocity. The third metric is very long baseline interferometry, or VLBI. By linking multiple DSN antennas together, engineers can compare minute differences in signal arrival times to pinpoint the spacecraft's exact angular direction. These 3 metrics, time delay, Doppler shift, and VLBI, are fused into complex predictive models that account for planetary gravity and solar radiation pressure, allowing mission control to steer the spacecraft. Steering a probe through the solar system requires the active, continuous calculation of relativistic physical forces. This established architecture is now facing a severe bottleneck. Modern deep space instruments are generating exponentially more data than legacy systems can handle. The traditional S, X, and Ka radio frequency bands utilized by the Deep Space Network are reaching their absolute physical capacity limits for bandwidth. Just as terrestrial systems are abandoning pure RF for quantum physics, deep space architecture is pivoting towards photonics. The Deep Space Optical Communications Initiative is shifting the transmission medium away from wide radio waves, replacing them with highly focused lasers. Because lasers operate at significantly higher frequencies, they allow for drastically higher data rates. The trade-off is that these optical links require mathematically perfect pointing and alignment to hit a receiver millions of miles away. From harnessing the subatomic lattice of a diamond to aiming laser arrays across the solar system, the future of navigation requires abandoning the limits of radio frequency to embrace the absolute physics of the universe.